Hello and welcome. There are many different types of graphs we can use to visualize our data. Understanding when and how to use graphs is a key skill set for the practice of continuous improvement. To illustrate the power of graphs, let's imagine it's Monday morning and our manager asks how our plastic molding process is performing. Specifically, she's interested in how consistent the weights of these plastic parts are. She shares some weight data of 200 parts that were randomly sampled and weighed over the last few days of production. It's very difficult to look at this much raw data and come to an accurate conclusion. As such, we decide to graph the data in order to make sense of it, using a standard histogram. And from this graph, we learn that our data seems to have a nice bell shape to it and that the sample mean is around 4 pounds. From just this one graph, we're in a much better position to explain to our manager how this particular process is performing. This is why it's important to learn when and how to use different graphs. Different graphs help us emphasize different characteristics of the same data. The choice of graphs or charts we use often depends on the type of data we have and the purpose of our analysis or presentation. Each form of visualization serves different purposes and is suited to different types of data. Some of these graphs work better with larger sample sizes, while others perform very well with smaller sample sizes. Let's review 7 of the most commonly used graphs and what they can tell us. The Pareto chart is a bar chart that's been sorted in order of decreasing frequency. This chart gets its name from Vilfredo Pareto, who observed in 1906 that approximately 80% of the land in Italy was owned by 20% of the population. We see the same principle at work in quality control when we see that approximately 80% of all effects come from 20% of the causes. Many people are familiar with this as the 80-20 rule. We often use Pareto charts in order to identify improvement opportunities, especially when we're dealing with defect information. In this example, we can see that the defect of scratches is highest and may warrant further investigation. The red line plots the cumulative frequency of each bar. Here we see that together scratches and chips account for 81% of all the defects. The next graph is a pie chart. We use the pie charts when we want to compare the relationship of parts to a whole. The circular shape and the individual sections look like slices of a pie. In this example, the team is interested in understanding the defect types across 3 different production lines. As we can see, scratches are indeed the largest issue across all 3 production lines. Next, we use the histogram when we want to better understand the shape and spread of variable data. The horizontal, or x-axis, of a histogram represents the scale of the data. This scale is then divided into equal intervals called bins. We might think of these bins as buckets that hold data within a specific range. For example, when using our plastic part weight example, we see that this bar is 33 units high since there are 33 parts that weigh between 3.85 and 3.95 pounds. The blue line helps us better understand the overall shape of the data. When our data are normally distributed, our histograms will generally have a bell shape, as we see in this example. Many times, our data may not be normally distributed. In some situations, our data may be bimodal, as shown here. This can occur when data from varying processes are combined. For example, the day shift operator may have a slightly different way of producing the same type of part when compared to their night shift colleague. Discovering this with the use of a histogram can be very helpful as we work to achieve consistency across all shifts. We may also see a histogram that is skewed. In this example, we see a process that's skewed to the right. We often see skewed distributions when dealing with boundaries. For example, if we're dealing with a measure of time, we could have a lower boundary of 0 seconds since it's not possible to go lower than that. While it's possible to create histograms with smaller sample sizes, we don't recommend this. As we can see from these 2 examples, the graph with a larger sample size of 50 gives a much better representation of the process than the one with a smaller sample size of 12. Instead, it's best to collect at least 30 data points, preferably 50 or more, when creating histograms. However, there will be times when we're dealing with a limited sample size of variable data, meaning the use of a histogram isn't advised. In situations when we're dealing with small sample sizes, we can use another type of graph called the dot plot. While the dot plot may not help us understand the overall shape of the data, we can discover outliers or where our data seems to be clustered in a specific region. In this example, it seems the region between 2.5 and 2.7 warrants further investigation. Let's assume our plastic part producing factory wants to quickly assess the consistency of 2 production lines. They collected 20 parts from each production line and weighed them. Since the sample size is less than 30, they shouldn't use a histogram. While they could use a dot plot, there was another graph better suited for this, the individual value plot. We can use individual value plots to compare a group of numeric variables. With these types of graphs, our vertical, or y-axis, represents the scale of data. Each data point is then plotted accordingly. In this example, we see that the part weights from line number 1 seem to be, on average, heavier and more variable than the parts from line number 2. The next graph is the box plot, which can help us see larger patterns in the distribution of variable data. To create a box plot, we start with an individual value plot, as shown here. Then we divide the data points into 4 equal parts, or quarters. We ignore any obvious outliers, such as the data point at the bottom in this example, when dividing the data into quarters. We then draw a box around the 2 middle quarters, which represents 50% of the data points. The middle line is the median of the data set, also called the second quartile, or Q2. The lower line is called Q1, or the first quartile, and 25% of the data points are below this line. The top line is Q3, or the third quartile, and 75% of the data points are below this line. The distance between Q1 and Q3 is referred to as the interquartile range, or IQR. We then draw lines from the edges of Q1 and Q2 called whiskers to represent the spread of the remaining data. It's important to note that whiskers never extend more than 1.5 times the interquartile range. So any point that falls beyond the whiskers is noted as an outlier. Here's what a finished box plot looks like. Box plots are similar to histograms in that they work best with larger sample sizes of 30 or more. And, like individual value plots, box plots can also be used to compare different variables. The last type of graph we'll review is the time series plot, which we can use to plot variable data in time order. For example, let's say our plastic part producers want to determine if part weights varies throughout the day. To do this, they collected part samples every hour and weighed them. Once they had enough data points, they created this time series plot. From this graph, we can see that parts ranged in weight from 3.5 pounds to 4.6 pounds, and that the time of day doesn't seem to have an impact on weight. Time series plots can also help us discover trends in our data. We may notice that our data trends downward or upward. Our data may also vary in a seasonal manner. For example, a retailer may see consistent spikes in sales every December, which is obvious when looking at this graph. As we can see, graphs offer a simple but powerful way to visualize our data and reveal characteristics that enable us to use it for continuous improvement. That wraps up our review of graphs. We'll see you soon.